So good morning, everyone. It's a great pleasure to have you as audience for this presentation. And as disclaimer, I apologize if you spot some typos because I have been kind of like compiling these slides as a concatenation of things I presented in various places to make it a better fit for the audience here. But I hope like typos or things like that are minimal. Well, I really hope because I sacrificed the visit to Ireland yesterday because of like. Thanks for introduction, also for invitation. Yeah, as many Iranian names, I'm originally Iranian, so I have a first name that is compound, but typically I go with Sadegh or Sadegh, if you will pronounce this way. So yeah, feel free to refer me to this. And feel free to raise your hand if you have question along the presentation. So this presentation is about online reinforcement learning, and we begin from tabular, and tabular here means unstructured, where kind of like the model of the environment can be stored in a table, basically. So we begin from tabular problems, and the focus will be on algorithm with the theoretical performance guarantees, and eventually tabular, along the way, tabular would fade, and we move to a structured problem. But most of the talk would be focused on tabular problems because we would like to build some, present some building blocks that would serve structured problems. I assume no background, but if you have any background on Markov decision processes or RL, that would be definitely helpful. And it happens that this talk happens. This talk is given after a couple of presentations on reinforcement learning, but maybe one key distinguishing factor is that this is online reinforcement learning, and as far as I know, the previous one were offline. But that would be a good takeaway, this distinguishment between the two. All right. So, yeah, we did not spend a lot of time on this slide, but as you know, many tasks in real life fall into this framework of online sequential decision-making problems. And they can be modeled as reinforcement learning. Reinforcement learning is not now a new term. It has been around at least for 30 years ago or so. But 3-4 decades ago, people would have to sell reinforcement learning because people would refer to it within different communities like OR, statistics, and so on, or control, as adaptive control or stochastic control. So all these are related in some sense, and I can even make this bridge mathematically. But as you see, reinforcement learning could be could receive applications that would range, as like fancy things like playing computer games. How to manage portfolios in robotics is quite relevant. In operation research, they have this classical example of inventory management that can be, in the face of uncertainty, can be addressed by reinforcement learning. I added this bullet because of many of you. So query optimization is also another thing that can be addressed by reinforcement learning. But I'm the least eligible person here to talk about query optimization, but on the MDP modeling side, I have arrived to this conclusion. It's really like maybe a viable solution. Some of these examples are fancy, like playing computer games, but we have good scenarios and good results from reinforcement learning when it comes to precision agriculture and farming. And also recently, LLMs also are kind of like reinforcement learning agents in themselves. So all these things, basically, mathematically, if you would like to model this, they try to solve some underlying decision process. And we have to kind of like eventually like set the stage for like the mathematical model we would like to discuss. And we need these minimal ingredients to discuss or to introduce a decision process. At least you need a notion of a state that captures where what is the current situation of your environment? What do you do in this current world? What has changed compared to last time a step in your situation? And in each situation, in each state, you have actions. You are given some options. You have actions to take, and you have then consequences of these actions. But then we discuss about these consequences. But one consequence would be that you receive a reward, an immediate reward, that indicates the quality of the action you have taken. Of course, it does not mean that your action would have just immediate consequence. It will have also long-term consequence, like in real life. But by this reward signal, we mean the stage reward, the instantaneous or immediate reward that you get. So an agent interacts with an environment, and in this kind of potentially ever-going loop. Basically, at each time t, it is in current state s of t, the current state of the environment. It applies, according to some algorithm, some action the agent applies, and in response, the environment gives a reward that at time t is denoted by r of t, and produces also a next state, which depends on where you are, where you have been before, 1 day ago, 2 days ago, or maybe from many previous steps, but also depends on the action that you have chosen at this time step. And of course, there is an underlying goal, which is often formulated in terms of reward. For example, it could be simply sum of rewards. So one simple example is this. Imagine you have a cardboard that could move in one-dimensional axis. It can go to left and right. And you apply some force to determine how fast it could move. And the goal is to balance this cardboard. The goal is to make this cardboard stay upright for as long as possible. So here, the notion of a state could be the following. Could be just the position of the cardboard. Could be not only the position, but also the angle denoted by theta. It could be more complex thing. It could be position, angle, but also the velocity of the cardboard. What action you have, you only can choose in which direction you apply the force and how the intensity of the force is. And reward, this is what we define. Reward we define to be, for example, 1 if the tilt is smaller than some threshold with respect to being upright, otherwise 0. For example, this threshold could be just 10 degrees. You consider when it is tilted beyond 10 degrees in either side, it's a failure, and you have to do game over. Yeah, basically, I have set things this in Word, and one key observation here is that in this kind of very, very simple block diagram, and could not be made really simpler, you have the interaction between these kind of 3 ingredients and have this key goal of maximizing a function of rewards. But one key point here is that observations, like states here, and rewards are generated by an uncertain environment, and it happens that the environment is also unknown. Not only the environment tends to be stochastic, like for example, if you apply one action at different time steps, it could, or at different states, it could have different consequences. But also, it's unknown. You have to try one action several times in order to have some estimate of the quality of this action in a certain state. So this is quite generic yet. I have not told you how this reward is generated. I have told you, what you choose now as action and where you are, and also where you have been before and what you have chosen before influences this reward. And also, I have not told how dynamics are determined, how this next state is determined by the environment as a function of the current state, current action, previous state, previous action, actions in 10 days ago, a year ago, and so on. I have not told that, but we have to now put some kind of assumption and restriction on this. So it happens that a categorization of these decision processes, which constitute here, we have so many decision processes that admit this kind of simplistic structure. So it happens that basically the way next state is generated and reward is generated is a good way to distinguish or to categorize these different decision processes. And one way is to just restrict ourselves to the Markov property. And if you're familiar with this thing, Markov chain, a notion of a mathematical object introduced by this Russian mathematician, Andrei Markov, it's the same thing. So under Markov property, the way the next state is generated only depends on the current state and the current state and current action. And conditioned on the current state and current action, you are independent of the past. So the current state is rich enough to decouple you from the past, basically. The same for reward, but I see some mistake because of LaTeX. Yeah. So the way the reward is generated, of course, potentially it could depend on the entire history from time step 1. But the way it is generated under Markovianity, it is that it depends only on the current state and current action. So conditioned on the current state and action, your rewards and next state are decoupled from the past. So how is that possible? Is it a realistic assumption? This is a big assumption, right? But as a matter of fact, we have a lot of decision processes in real life that admits this kind of like formulation. And it has something to do with richness of the notion of a state. And because of this, we no longer discuss about generic decision processes. We rather discuss about Markov decision processes, which are decision processes admitting this property. So you have to be patient with me for some few slides so that I introduce some notation for Markov decision processes and why this is important. Because a lot of reinforcement learning kind of like papers and algorithms, as a matter of fact, try to solve some Markov decision process under uncertainty, under misspecification. So give me just, just give me one VLDB paper that does query optimization in using reinforcement learning. I would tell you that, it's more than 90% that they cook up some MDP, and of course it's under kind of like some good justification. And of course, they cannot directly solve the MDP because the MDP is with unknown parameters. And because of this unknown parameter, they have to use reinforcement learning to solve the MDP by trial and error in an offline manner or online manner. And this could be a good takeaway from this presentation, basically. So a Markov decision process can be modeled in the simplest form by a tuple, a state space, action space, transition function P, and reward function R. A state space, here we denote calligraphic S to denote the state space, has some size S, action space size A. There is this P transition function that determines what is the probability that you would move to another state S prime, conditioned on state S and selecting action A in this state S. And by Markov property, we know that there exists this probability. And there is this reward function R, tells you what is the reward distribution under a state S and when choosing action A in this state S. Of course, in general, a state space and action spaces could be finite. For now, we restrict to finite. They could be infinite but countably like discrete, but they could be even continuous. So you have good freedom on this definition. And how interaction with MDP works, typically we have the same like black diagram I showed you before. The only difference and only restriction is that now, when you choose action at time t, the reward that you get comes from a distribution or could be fully predicted by only knowing the current state and action. Of course, the state is something you observe. And the next state is determined by your current state and current action in a probabilistic manner, but you are decoupled from the past. So this interaction loops goes for not forever, but for t rounds. But this t could be yeah. We discuss it in the next slide. But for any t, whether it's infinite or finite, known in advance or not in advance, this interaction generates a history or trajectory, a state action reward, a state action reward, a state action reward, and at time t we have all state action rewards chosen so far, including the current state where we are. Now we are ready to choose action A of t based on this history or based on some simple rule. Here we can talk about the classification of MDPs just based on horizon. So if the interaction horizon is some finite number, we have finite horizon MDPs. We could have infinite horizon, but with discount. And we could have infinite horizon and without discount. So here we have discount factor, and it allows us to kind of like have some finite objective under some nice regularity assumption, some mild regularity assumption. But because of discount factor, but in the undiscounted case where basically discount factor is just 1, you need to move to kind of like average performance criterion. Anyway, the key takeaway from this slide is that when you have some MDP, you have the agent has some objective. And the objective could be, for example, any of these. So the underlying maximization problem could be to solve the reward you obtain over some finite number of rounds, or some infinite number of rounds, but under discount, or under infinite number of rounds without discount, but in some average sense. And in this talk, this third class is what we consider. We look at average reward MDPs, and this is basically those MDPs where the objective is to find a good decision-making behavior or policy under which the average reward in the long run is maximized. You would like to find a career plan so that in the long run, I mean, in the long run could be when you are 100 years old or could be 8 years old. It depends on what is the how accurate is this long run is considered. You would like to arrive at a good stage where per month, for example, you have your salary is maximized. It's in some sense it's like that. So does this infinite horizon a good reflection of reality? I mean, mathematically we are quite happy with it, but nobody has ever seen this infinite horizon. But as a matter of fact, it happens that they offer good approximation of tasks with long enough or some large horizon, so that some stationarity behavior is observed. Anyway, some examples, and I can pass over these examples very quickly. So this is the grid world example, the maze you have seen. The goal is to find the shortest path from the red to yellow. And of course, not all the tiles are shown here. So for example, this tile is one state, this tile is one state. So like boundaries of, I mean, like lines of tiles are not shown here, but this is it can be modeled using an MTP with 20 states. And in each state, we have the cardinal or compass direction, up, down, left, and right. So the failure is slippery. For example, under the action, for example, up, in some state, you could move in the intended direction with some probability like 70%, or could ended up in the same state with 10%, or moving in perpendicular directions with probability 10%. Reward we define to be everywhere 0, except in the final destination, which is yellow. So you can discuss it in the kind of like episodic task, but we are interested in this as a repeating scenario. Once you are in this yellow, there is a game over, and you are brought back to this thing, and the game is over. So now, if you consider that if this game is repeated 400 times, you can consider this to be approximated well enough using an infinite horizon MDP, basically. Even though there is some notion of finite length episode, but this episode length could be random. And a better way to model it is using an infinite horizon MDP. So you might say, who cares about this simple game? But as a matter of fact, it could be a small abstraction, or kind of like some abstraction of, like transmitting a large number of packets through some network that has some uncertain kind of like transition to a destination. And you can add further constraint. You can say, like there is an electric car, and eventually the car has to be charged also, like this car. And once the packet is transmitted, there is a fast route from here back to yellow. I might have mixed up destination and initial state between yellow and red, but I think you will get which one is which. Coming back to this card pool, the question is, what should be the right notion of a state X or X and theta? So either of them could be good notion of a state. But as a matter of fact, in order to yield an MDP definition, the notion of a state must contain these 4 components: position, velocity, angle, and angular velocity. And because of physics dynamics, we would know that next state, which is next position and next angle of the card pole, would be only dependent on the current value of this guy. Okay, another example is query optimization. Basically, the goal would be here to find a query plan minimizing long-term execution cost. So please, I'm up for heated discussion, but do not press me with this example because I know you can. But yeah, so these 2 papers I chose are from VLDB in 23 and 2019, and although they do some MDP formulation approach and do RL, it's at VLDB. So of course, to model this as a Markov decision process, the state could be the partial query plan, the subtree that you have built so far. If you say I'm at some stage T, I have began from empty thing, and a subtree is already developed. The partial query plan could be seen as a state. The action is like join order decision, and reward could be, because we talk about minimizing and reward is a positive, is in a maximization direction. The reward could be negative of execution cost, but you can add also other thing for the reward. You can also, if you will, you would like, and if you have, you can add also constraints that you have, and that would still make the problem an MDP formulation. Okay, so now back to boring part, a bit more math, but within some few slides, with maybe just 3 slides, we will arrive at how these MDPs under known parameter setting is solved. If you're familiar with MDPs, you know that actions in MDPs are taken according to some policy. The policy could take one of these 4 forms, could be a stationary deterministic, could be a stationary randomized, and so on. So for the purpose of this talk, and even for the purpose of reinforcement learning, there is a rich structural assumption, result, not assumption, that it's enough that you just consider the simplest form of the policy, which is a mapping from a state space to action space. Basically, it tells you, if you're at the state blah, tell action, certain action. It could be, for example, go right. If you're in the corner, for example, turn left. It could be simple as that. But one level up in the hierarchy are policies that would map from states to a probability distribution over action. So it randomizes a little bit. Although we will see this randomization for algorithms are necessary, but not for the eventual kind of policy to be sought. But we have these sets of policies, basically. So we need to rank different policy in terms of their quality. That's why we introduce some notion of value function. But for average reward MDPs, we have 2 notions of value function, and the one that is must to introduce is the notion of gain. So the notion of gain is the amount of reward that you would achieve per step under policy pi, starting from some initial state S. So for a given policy pi, you define this to be the gain function. It's an ugly definition, I know, but it's useful because the complex objective of the MDP could be just reduced to finding a gain optimal policy over all possible policies, basically. So this policy that maps from histories to probability distributions over actions, basically, are more complex policies. And seeking a policy that achieves this optimal gain is what we would like to perform in this life. So this is the difficult optimization problem because it involves, even in a non-parameter setting, it involves expectation, and this expectation over infinitely many trajectories and over considering also the limit that t grows to infinity. But luckily, in many kind of sensible for us decision-making scenarios, we have to deal only with MDPs that have some notion of weak connectivity. And these are MDPs under which, The optimal gain does not depend on the starting state, which is good. It means it doesn't matter basically where you're born. Like eventually you will get the right person. I know it's not realistic, but like mathematically there exist these notions. Yeah. But the good news is that under this weakly communicating MDP assumption, which encompasses many applications, there exists at least one stationary deterministic optimal policy. This means that in this previous optimization, instead of looking at policies here, which are infinite, you could look at policies here. You could forget about your history. There exists a policy that looks at where you are and commits to a deterministic action. So we were not aware of this before like 40s or 50s, more or less. This is a result that was proven around that time. If you have heard of Bellman, this American mathematician who kind of like proved these sets of results, basically he gave us equations that would allow us to find this a stationary deterministic optimal policy, and consequently to solve MDPs. So basically, we have Bellman optimality equation for a given MDP, and the only necessary assumption is that it's weakly communicating. It tells us that under a weakly communicating MDP, the optimal gain and another function that is another value function, optimal bias function, satisfies this fixed point equation because it tells you the optimal gain and optimal bias at the state S is determined by the reward and transition, and also like this optimal bias function at other states, including a state S. So it's a set of fixed point equation. It's implicit, but this can be solved using some very, very simple iterative algorithm. That is an extended version of, or like modified version of what Richard Bellman himself introduced in 1957 for discounted MDs, for simpler decision-making processes. And by the way, notice that this is after the time we invented computers. So like we managed to solve this afterward. So the algorithm could be as simple as that. You start from some value guess, and you iteratively apply this equation, and you stop as soon as this stopping criterion is met. And if you do not believe me, this is a simple algorithm. Like even I, that I'm not an expert in Python, could implement this in kind of like 10 lines or something. So what is this slide, which is our last MDP slide in summary? You can cook up an MDP for many real-world tasks. And one of the most difficult notion is average reward MDPs. And for these complex average reward MDPs, there is this simple algorithm that solves the MDP. Basically, you do this, and this stops eventually for some precision that you choose, some epsilon that you choose. And as soon as you take the argmax with respect to the final value output, which is Vn, this output policy is either coincides with the optimal policy or a good approximation thereof. And this approximation could be made better and better with the smaller epsilon. And the convergence is also like quite fast. Okay. Now what? So we know how to solve MDPs. And these are kind of like where we know how dynamics of our decision-making process works. Basically, if you know how it works, you must not do reinforcement learning. You must just do value iteration. But in a lot of scenarios, the word is uncertain or the word is misspecified. You don't know what is P and R, because if you look at value iteration, you would know you need to know the knowledge of R and P. This is something that is not precise enough. We do not have enough prior knowledge about this. And because of this, we do reinforcement learning. We know there exists some MDP that accurately models our decision-making scenario, or our problem at hand could be framed as a Markov decision process. But we don't know these parameters, and because of this, we do RL. So In RL, basically, we do the same thing as we do solving MDPs, except for the fact that P and R are unknown, or not completely known, or not perfectly known. And yet, we wish to learn an optimal policy or near optimal policy. But what do we do that when we don't know P and R? We don't know P and R, but we have the environment. We can sample this P and R from the black box. The black box is not revealed to us. And we can collect data from the environment in order to estimate P and R or do something else. And in doing that, basically, you can distinguish two big stream of works within RL. Offline reinforcement learning, in which you have pre-collected data sets from MDP. This data set could be bought from a third party, or you could send some people in the field who would collect this data set and bring it to you. And once enough data is collected, you are disconnected from the world, from the MDP, and you would find a near optimal policy in some way using some algorithm. This is this black diagram, but please don't read this text because it would be confusing. So first, you have a data collector mechanism. It could be one guy who is expert in data collection who would go to forest, who would go to, I don't know, like Amazon River and would collect because you're not working at a high-tech company, but rather you're working at some, I don't know, like some environmental thing. The result would be a data set. And this data set is either sold to your company or, is collected by the same guy from your company. And this data set is passed to a training algorithm. It could be whatever complex learning algorithm, and we do not discuss about it. Previous guys discussed about it in the earlier session. And the output is a trained or learned RL agent. And now the learning is done. And you deploy this agent in real world. No further exploration. In contrast, we have online RL, our focus, where there is no separation data collection strategy. You have agent that basically begins from potentially no knowledge about the environment, but tries to do by trial and error, meaning that the agent and the algorithm that trains it is within the same box. And it has this simple life. There is no training phase and no kind of a deployment phase. Training and deployment is mixed because we believe there is a single life and every single mistake you make in your life counts. So learning from scratch, no training phase. And instead of a data set that you could buy or you could collect by your guys by some special method, you have an ever-growing history denoted by H of D, a state action reward. A state action reward that you would have to use to do what? To do trial and error. This means that in this single life, you must do both exploration and exploitation. At the beginning, you have no knowledge about the environment. You must explore, it's like you would like to learn how to ride a bike, you have to explore, you have to pay the price for it. But eventually, you build some knowledge and you start exploiting. But if you exploit too much, maybe you must not commit to exploitation too much. And you must not explore your entire life. It's not a good idea to search for the right match until you're 50, right? You must do some balance. Okay, key challenge in offline RL is lack of exploration, because once your data set is collected, you are detached from the environment. It's too late to collect any further data. But on the other hand, in online RL, you must decide when to explore and when to exploit. And this could be more challenging. Okay, this is key slide, because every paper you open could fall either in one of these or could be related to a sister setting of this. So we talked about exploration and exploitation, and this is the key thing to be balanced in online RL, but we need metrics to quantify the quality of exploration and exploitation. And again, if you open an online RL paper, basically these are the three metrics that are considered. Basically, one is convergence, whether a near optimal policy is eventually learned under your exploration trade-off. Of course, if the trade-off is implemented badly, you would not converge to an optimal policy. Sample complexity is another one. tells you what is the amount of data you need to learn a near optimal policy. If you do a bad exploitation trade-off, it takes you a lot of samples, But an algorithm that does a good implementation of, or a good balance of this would do it quite fast. The most precise one is regret, and it captures the amount of rewards lost because of exploitation. Actually, because of your exploration, because the exploration could lead to these bad rewards. And this is where we focus here, and you will see the difference, the definition. So I do not present the definition of the other two, but this third one, because this is the most precise, and we will see why it is the most precise. It's denoted by regret, and it's a function of time t, but for some MDP at hand. So it compares the reward in purple that you collect in t time steps, and this t can grow large, to that is obtained by an oracle policy who is aware of the optimal policy from day one, who would know how to ride the bike in an optimal manner and would do it, would exploit already from day one. So this is what you have control over, and this is something out of your control. So if you minimize regret, it's clear that you are maximizing reward. And yeah, like if you look at this figure, the optimal policy, the oracle would receive this constant kind of like average reward per step. And if you look at the area under this red curve, it would be this one basically in expectation. But the agent, which is you, basically at the beginning has some bad performance, but along the way, it manages to learn good policies, and in terms of quality, it approaches the quality of the best policy, hopefully. And if you look at the area surrounded between these two curves, this is the amount of reward in expectation you lost because of not knowing the optimal policy. And the regret captures this area, and we would like to minimize this reward loss. So we would like to minimize regret, and it's equivalent to also maximize the reward. And mathematically, we are interested in algorithms that have regret that is sublinear, or would be little o of t mathematically. So we call this algorithm sublinear regret algorithm or no regret algorithm. Because if regret grows linearly, this means that this area would grow quite big. So it's a measure that the area would be under control. So in summary, we have offline RL versus online RL. And for online RL, it's very key to have a good measure to quantify exploitation trade-off. And the most precise thing is regret, which captures whether you're making too many mistakes or not. It captures what is the kind of like this quality. Okay, now I would like to present some algorithm that would do a good job in terms of regret for unstructured problem, and the focus would be on tabular problems or unstructured. And tabular comes from the fact that you can store MDP parameters in a table. From one state action to another state action pair, there is no relation. So you have to store all these numbers. There is no data structure in data representation of the MDP that you can use. So as a warm-up, we talk about certainty equivalence principle, and this is the principle our ancestors knew from 1,000 years ago. Like it says, in an unknown world, act as if your estimate equals their true values. We don't know what are P and R, transition and reward function of the MDP, but at some point we have some estimate, and let's trust this estimate. Let's replace in this MDP definition, instead of unknown P and unknown R, let's replace whatever estimate we have, and if these estimates are consistent in some sense, some mathematical sense, maybe we will be doing good. So the first idea would be maintain some estimates, whatever you like, but please don't go for stupid estimates. Go for good estimates. Consistent. I mean, you have infinitely many choice of estimators, but for example, maximum likelihood estimate would be a good thing. And formulate the empirical MDP. You know what is the status space and action spaces are, but instead of P and R, P hat and R hat at time t. And solve this MDP by, for example, value iteration, and apply this policy. Choose your action at time t using this optimal policy at time t. And using this action, your history will grow, right? And then you collect new data, and your estimators are refined, and go on, go on, go on. It's a very naive idea, and if your estimators are good, maybe it's not that bad an idea. But you know this idea will go to the wall. Because you could be quite unlucky. You could, estimators would be more precise if you have access to a large number of data that is collected from everywhere in the MDP. And this is not something you always have, because you apply this policy, and this policy may not guide you to go to a good part of the MDP. And because of this, there is no exploration-exploitation trade-off. You're just exploiting. You're just exploiting, and there is a chance that you get linear regret. You make a lot of mistakes. You could be unlucky. I know this is what our people do in life, some people, but it's because of luck. If they have another life, or if some other people would copy their decision-making, it would be a bad idea. A slightly better idea would be doing certainty equivalence plus trembling hand. Just, commit to this exploitation policy, but eventually, sometimes try to do random actions so that, you explore other part of the other options at different states. Well, it's one of the simplest idea, I could say, that would do some exploration-exploitation, especially if epsilon would decay with t at some good rate, but it's not empirically performing well. And we need much more elegant principles, such as optimism principle that was developed by mathematicians in 1985 for the problem of bandits, which are stateless MDPs. So the optimism principle, instead of certainty equivalence principles, tells us the following. The world is unknown, and you are trying to solve some maximization problem. Consider the world, this unknown world, is among some plausible models you can maintain about the world. Consider the world is in favor of you. It's the most plausible. You have the most president, in country 1, country 2. Everything is peaceful. And everything leads to, if you have trade with another company, it is in the direction of your highest reward, but among all plausibles one you can think of, go to the moon. So how it is synthesized in our case? So instead of just relying on estimates R hat and P hat, now we have to build set of plausible models for the environment that would be consistent with the knowledge we have. So instead of just relying on this estimate, we build confidence intervals around these estimates. And these are high probability confidence intervals, basically. And so we do it for reward function at every state action pair, transition function at every state action pair. I can't talk about all these mathematical details, but I simplified so that the focus is not lost, with some radius, beta and beta prime, that would shrink over time, would shrink as your history grows, basically. So altogether, we can arrive at a set of plausible models of the environment, and this is a set of all candidate MDPs that define over the same state and action space as the true MDP, which these two we know. But candidate P prime and candidate R prime are taken within the confidence set. So we know how to build this confidence set, and then we know how to build this model. But there are infinitely models in this. So if these confidence sets are defined using some mathematical principle, although this set of model is infinite, it traps our true MDP. We don't know the true MDP, but we know how to trap it in some set. And if this set shrinks over time, maybe we are doing well. But how to apply optimism? Optimism tells you, choose among this set an MDP and a policy in that MDP that has the highest possible, reward for you. And this is the way you do, basically. You maximize not over your gain function, but also over all possible MDPs in this thing. This is how you implement optimism, one way to apply optimism in this case. It appears to be a complex mathematical optimization problem. Yes, it is, but because of this shape of the confidence set that has L1 inequality and, like this, it can be done by an extension of the value iteration called extended value iteration. And basically, the algorithm could be as simple as this. Of course, I hide difficult things in some routine called EVI. But basically, it would be like this. What I explained was just an algorithm that was developed in 2010, UCRL2, by some guys from Austria, Yaksh et al. Basically, it does regret minimization. It does exploration trade-off in a wide class of unknown MDPs in the average reward setting. And it begins from empty history. And in each time, it computes these empirical estimates from the history and maintains and implements this extended value iteration to decide what is the policy at time t, and chooses action according to this policy, and then collects reward according to this policy and next state according to this policy, and increases the history. But of course, you need not compute the policy at each time, because your confidence set would not change substantially when just one piece of data is added to your history. But rather, you can do lazy update. You can do whenever, for example, number of state action per visits is increased by 100, or the length of history is doubled. This is very, very simple algorithm. And if you see, instead of this input parameter, which is formulating your confidence, it does not need any parameter tuning. And it took us up until 2010, until when we know how to do this. Before showing regret guarantees, this is like in this grid wall task, like with 95% error bars. The average of 30 experiments of UCRL2 is shown on this grid wall. So basically, our agent does not see the walls unless it's in the vicinity of the walls. It does not know what is transition function. It does not know what is reward function. It begins really, really from scratch, and it does only know that there are these 20 states and there are 4 actions in the states. But it learns to minimize its regret. It learns to achieve a sublinear regret. You see that the regret grows sublinearly. At the beginning, it is linear because it does a lot of exploration, but at some point, it begins exploitation and mixed with exploration, and that's why you see kind of like a bend in the curve. The blue is UCRL2, and the black is a better algorithm by myself and colleagues. But yeah, like we improved, but I was lazy to remove one curve. But what about theoretically? Theoretically, we have this result, because the focus was theoretical RL for these tabular problems, right? So for any algorithm, this is lower bound, yeah. So under UCRL2, in any MDP with S states, A actions, so finite MDP, and we need another kind of like thing that measures the diameter of the MDP, diameter D, which is finite. The regret under UCRL2 would be upper bounded by this with high probability, and non-asymptotically. You need not wait until infinity, so that the regret is settled. So basically, it tells you the amount of reward you lose because of not knowing the optimal policy. If you begin learning from scratch, of course, would grow with time, but sublinearly over time. Not proportional to t, but proportional to a square root of t. But of course, it depends on how many states there are, how many actions there are, as well as what is the kind of like the diameter of your MDP. How difficult it is to reach from, the farthest point from your MDP to any given point. Okay, the question is whether this could be done better. You cannot do better than the square root of t, because there is an information theoretic lower bound telling that give me an algorithm, any algorithm that does this exploitation trade-off, And there exists an MDP that challenges this algorithm so that it incurs this regret, at least. So you cannot do better than a square root of t. This is, yeah. And if you compare what is this lower bound and what is UCL2 regret, you would see that there is a gap, but in terms of t, there is optimality. Okay, is it really something new? So early literature on this dates back to 97, 90, I mean, like 97, many things happened. So yeah, I know this group who did this quite well. But they did only with asymptotic regret guarantees. And these are algorithms would not perform well empirically. But we knew how to do it. Of course, these are not computer scientists. These are basically statisticians and mathematicians. And computer science began working on this since 2005, 6, and UCRT was born in 2010. You see, there is a 2. What is this 2? Because the first try did not really work, and the second try worked. But variants of UCRL2 were presented, and like maybe the most recent variant that achieves optimal regret was just a year ago, basically at 224, that achieved this lower bound. Basically. Okay, so even though it was kind of a tabular problem, we really didn't know how to solve it mathematically really well, or in a reliable manner empirically up until 2010, and the gap is more or less closed only recently, basically. Of course, the same picture for discounted MDPs and infinite and finite horizon MDP was closed rather earlier, but not much earlier, basically. I know in terms of time, I might not be at 5 minutes. Okay, this is what more or less I mean. So let's move on to structured problems. So far, I discussed the case where, like I just showed you just 2 examples, basically. I ignored any structural properties there is in the environment. And I would, I would ignore structural properties, but we know these structural properties exist. But let's begin from this motivation that in real-world problems, a state space is huge. It's not large, it's huge. It could be even continuous, like, for example, this car control problem. The state involves, the position where you are, and there are infinitely many positions, right? And in computer games, the state could be huge, basically. So we have seen that regret guarantees would depend on S. Well, not S, square root of S, but still. And we know there exist success stories in kind of like problems that would have a state space as this large, right? So what's the magic? So in this, there exist many states here, but also a rich notion of a structure in these problems. And the key is either to use the structure that exists or impose. Let's think as if there is a structure, or even the structure is not completely there, but approximately is there. So let's impose some structure, and this is what, for example, deep reinforcement learning does. It assumes there exists this structure, and for example, the structure in the value function, and neural network as a nonlinear function approximation could be used. And that's why, even though like they attack the problems this large, they can derive meaningful results. Example of a structure that we can discuss now, there could be a structure in model, meaning in MDP parameters. It could be a factorization model, linear mixture, equivalence relation, Lipschitz smoothness. But the structure could be assumed directly in the value function, in the gain function, or the value function associated, or the way we can define, for example, Q function here. It could be, for example, smoothness of associated Q values. So if you look at the literature, either they try to compress state and action spaces. It doesn't matter if they're continuous or huge, and then they compress it and apply RL to this smaller compressed problem, or directly, without compression, apply algorithms. But in the algorithm, there is a mechanism that would respect this structure, would exploit this structure. Okay, let's have some concrete example. One example is factored MDPs, and this is where you have a vectorial of a state space. I mean, in the cartwheel, you remember we had 4. So, okay, the vectorial state space does not mean that there is a structure, but in factored MDPs, there is this assumption that the transition function admits a product form. For each state, there is a set of parents that would determine how the nexus is determined. Yeah, this is some sort of conditional independence structure, and this is often represented using some dynamic Bayesian network, if you have heard in other contexts. For example, here it tells us that the next value of first state variable is only influenced by first and second. It's independent, condition on this, it is independent on third and fourth. Typically, this graph is sparse, even as sparse as what I've shown. And this sparsity has to be kind of like leveraged in order to speed up learning. If you see the size of a state space could grow exponentially with the number of factors or with the number of state variables, but because of this structure, there is a hope that learning can be done much faster. One example, in an energy minimization in a smart home, you can consider a state representation comprising 5 variables: indoor temperature, relative humidity, outdoor temperature, number of people inside the room, and HVAC setting. And if you think about it, the outside temperature has nothing to do with inside temperature, right? The next value of outside temperature is a function of what the outside temperature is currently now. But what about relative humidity? The relative humidity is in the next step is a function of now, the humidity now, what is HVAC is set to, and the number of people. And it has nothing to do with the outside temperature, because it is already captured with the relative humidity at this current step. And if you draw, so I have not shown all the relationships. If you draw the kind of like the bipartite graph corresponding to this one, you would see there is some sparsity. And because of this sparsity, you can think of an adaptation of UCRL2. Instead of building confidences for P, just build confidences for these PIs, and impose the factorization structure. Since this factorization is known to you, it is the assumption, in the set of models. So you can have much smaller set of models compared to vanilla UCRL who would ignore. And this is what is done in the literature, and mostly, including myself, people try to look at this. And if you look at empirical performance, there is massive improvement over structure oblivious algorithms. Another one is when you have linear structure, and I'll wrap up in some quick minutes. If you have some features for different state action pairs, d-dimensional features, and some unknown parameter, you can have reward function that can be represented using this linear mixture model. The same can be done for transition model. And an adaptation of UCRL2 could be, instead of estimating R and P, estimate lambda and theta, because uncertainty is up to these parameters, not for the entire reward and transition. And make confidence sets for theta and lambda, not for P and R directly. And if you look at this, the regret guarantee of one of the successful algorithms in the literature, which are recent, would depend on the dimension D. It would not depend on the size of state action spaces, S and A. So a state action space could be infinite, but you would have a finite regret. Okay, now you see that's why I presented UCRL2, because you have it as the synthesis of optimism principle, and you modify this algorithm. Of course, the modification is the big question, but it allows us to really depart from tabular models. All right, another example was reward machine, but I jump over this because I think it was introduced before. So some quick key takeaways. Average reward MDPs could offer a good model for many real-world applications, and these are not well explored because people just land on discounted MDPs or finite horizon MDPs. But these, for many reasons, could represent a better model of the environment. And in average reward MDPs, in the corresponding RL problem, regret as a suitable performance measure to quantify performance of your exploitation trade-off, because that's key for online reinforcement learning. In unstructured MDP, this regret is information theoretically unavoidable, but we have algorithms that achieve this non-asymptotically. And in implementation, they are quite reliable in a sense that, like there is no parameter tuning, and you can really, really, really implement what the theory tells you without any kind of like modification of constant or so on. And that's quite good news. And in a structured problem with potentially infinitely many states or actions, it's possible to achieve non-asymptotic regret bounds growing with ambient dimensions, independent of size of state and action spaces. Thank you for your attention, and thanks for tolerating your patience with me. I hope you have some good takeaways from this, but please feel free to also raise questions or kind of like bring it up also to the panel, these questions. Thank you.
Thank you so much, Sadegh. Any questions? Let's go in order.
Thanks, actually, very clear talk. I certainly have no regret attending it. So you presented for us this notion of regret to measure like the loss in rewards. But I was wondering, this setup seems like an imperfect information game where we don't really know the real reward function. I was wondering whether there is like some information theoretic measure, like wisdom or amount of information that we are gaining about the real reward function that we can use in addition to regret, basically to balance exploration versus exploitation. Is there such a notion?
So if I got the question correctly, you talk about a game theoretic situation, right? Or you mentioned a perfect information game? Or?
Imperfect information games. Like regret just measures how much we are losing in terms of reward, but I was wondering whether there is a direct measure of how much information we are gaining about the real reward function when we take an action.
Okay, so my answer would be on two different facets of the question, and maybe one is more proper than the other. So for games in particular, I'm talking about games where there is, you said game or gain?
Game.
Game, yes. So this is not a game with the environment, right? But it could be modeled as a game with the environment, but instead of a Markov decision process, I mean, I'm talking about the case where there are more than one agent, 2 agents. So it would be a Markov game, and you can define regret on those Markov games. So that's, I mean, there are extensions of this result for Markov games, basically. You have notion of regret for this, and the goal would be to arrive at some equilibrium point, so the objective would be a bit different, but more or less, there is a way to measure exploitation trade-off there. But if the question concerns the fact that how accurate now my learn reward function is, the question is, why do you care about an accurate reward function? Because it's not an estimation problem. If it was an estimation, I mean, you can frame estimation problem as kind of this, because then the question would be to learn the reward function accurately well across all the state action pairs. But that would be more or less an estimation problem, and of course, the goal would be to use your finite sample budget to kind of like distribute. Okay, I hope I don't go too far from what your question meant.
Yeah, thanks. That was very helpful. We will pick it up more during
that. Yeah, sure. Let's.
So thank you for your talk. My question is just connected to what Mahmoud just asked. And actually, it's about the optimism principle. And I kind of missed the intuition behind that concept, which I think consists the backbone of all the solving algorithms you mentioned. So could you elaborate more on that?
Yes. So basically, in optimism principle, I mean, one level up this certainty equivalence, it is, like that. You would like to be more elegant than just looking at point estimates, p hat and r hat, right? Because p hat and r hat are point estimates, so just numbers, estimates. but they do not tell you how accurate are these estimates, right? So one way up the hierarchy is to look at not only estimates, point estimate, but also on the confidence intervals. And then like, I mean, imagine we are doing together. Let's look at confidence intervals, and then we combine these confidence intervals, and then using the history at any time, we can think about a continuum of the models of the environment. Of course, this continuum would shrink over time. But the optimism principle tells you how to do this from this point onwards, because there are infinitely models here. Shall we go on the average model? Shall we go on some random model here? The optimism principle tells you, go for the highest reward that you can get from any MDP here. It tells you the following, basically. I mean, you can go for pessimism. You can go for the lowest reward just to kind of like safeguard yourself, you know. But your question could be also like, okay, intuitively, why it works? Intuitively, it works because under optimism principle, if we happen to choose an optimal a policy that coincides with the optimal policy, it doesn't matter if the model coincides. There's no regret because you have chosen optimal action. But if you choose a suboptimal policy, you know, like you would prune some models from this model set because your confidence intervals would be, because you collect data anyway, right? But sometimes this bad collection, sometimes you're in a bad relationship, but you learn a lot about, you know, like the other gender, you know, right? And so the optimism principle, it's mathematically works in a way that even though when you explore, you know, like you pay a penalty for that, you incur regret, but while incurring regret, for the next time step, you discard some of these models that are known to be bad models now. And I'm telling you, without looking at kind of like really proof outline, you cannot really see why it is, you know, like why it is like that. But yeah.
Any other questions? No?
Maybe just one addition, just very quick parenthesis. So in offline reinforcement learning, you need pessimism. It's, in offline. At least one principle that works is, I mean, you could follow the same thing, but you would have to go for pessimism, you know.
Can I ask a profane question?
Of course.
In your grid, why could the red tile not move diagonally? When you put up the grid with the red tile and the yellow one, wouldn't the shortest route be diagonal?
That's a very good question, because it's because once you are in this tile, you know, like you can go perpendicular directions. That's yeah. You can have. I mean, in another problem formulation, you could have these alternatives. Yeah, you could go southeast, for example.
Okay, so another round of applause for the wonderful talk by Sadegh.
Thank you.
Okay, now we're having